There are two useful things about permutations which we're going to discuss in this video. The first is that the inverse of a permutation is another permutation, and the second is that the composition of two permutations is another permutation. So let's begin with inverses. If you have an invertible function, so let's say f, then its inverse is also invertible, because if f has inverse f inverse, then f inverse has inverse f. So the inverse of a bijection from x to x is just another bijection from x to x. That means that the inverse of a permutation is another permutation. So let's take as our example this function s, which is a permutation. It belongs to S4 as a permutation of the set 1, 2, 3, 4. What can we say about the inverse of s in two-row notation? So it's got to have some kind of two-row notation like this, but what will go on the bottom row? Well, what that two-row notation for s means is that s of 1 is equal to 2. So that means s inverse should send 2 back to 1 again. So we can put a 1 in here. The second column of our two-row notation means that s of 2 is 3. So that means s inverse of 3 is 2. The third column tells me s of 3 is 4. So s inverse will send 4 back to 3. And finally, actually, if you think about it, you don't need to do any more calculations. You know that the things on the bottom row must be the numbers 1, 2, 3, 4 in some order. So actually, I know without doing any calculations at all, I know there must be a 4 there. But of course, we could work this out from first principles. The two-row notation for s tells me s of 4 is equal to 1, so s of 1 is equal to 4, which is the entry that I just filled in. So if you think about it, what this is telling you is that you can get the two-row notation for the inverse of s just by swapping the rows and then reordering the columns so that the top row is in the correct order. So let's record that. The two-row notation for the inverse of a permutation is obtained by swapping the rows and of course reordering the columns so that the top row goes 1, 2, 3, 4 in the correct order. And you can see how that would work in our example. So if we start off with s, which was 1, 2, 3, 4, 2, 3, 4, 1, and if we then swap the rows, I've got 2, 3, 4, 1, 1, 2, 3, 4, and now if I reorder the columns so that they're in the correct order on the top row, I would have 1, 4 first, and then 2, 1 next, and then 3, 2 next, and then 4, 3 last. You can see that really is what we got when we actually worked this out from scratch. Okay, so that's how we can find the inverse of a permutation when it's given to us in two-row notation. We're now going to use another result that we saw about compositions of invertible functions. In the previous video, we showed that if you've got two functions f and g and they're composable and they're both invertible, then their composition is also invertible. That was the shoes and sock things. If f and g are invertible and g composed with f makes sense, then g composed with f is invertible, and its inverse is f inverse composed with g inverse. So that tells us, because our permutations are functions from a set x to itself, that the composition of two permutations of x is again a permutation of x, because the composition of two invertible functions is an invertible function, so the composition of two bijections is a bijection. So we should be able to work out the two-row notation for the composition of these two permutations, s and t, which belong to the symmetric group S3. But let's try working out two of these compositions. We're going to do s composed with t, and that should be a permutation in S3, so it should have a two-row notation like this. And of course, s composed with t means it means the function whose rule is do t, then do s. So let's work these things out. S of t of 1. That's going to be what goes just here. And I'd like to know what it is. So s of t of 1, what's this? Well, t of 1 is 2. So that's what this column here is telling me. So I've got s of 2. And t of 2, s of 2 is 3. That's what that column there is telling me. So I've got 3 here. Okay, so I can put a 3 just there. Okay, similarly, let's do some more. S of t of 2 is S of t of 2 is 1. The middle column of t tells me this, and S of 1 is 2. So I've got a 2 here. And finally, S of t of 3 is S of 3, which is 1. And again, I didn't actually need to work that out because I know that the things on the bottom row must be the numbers 1, 2, 3 in some order. So when I've got to the last position and there's no 1 on the bottom row, well, it must be a 1 going there. Okay, so however we do it, that is the 2-row notation for S composed with T. Let's now do the other way round. So we're going to do T composed with S. Again, we'll work out the 2-row notation for this composition, T composed with S, and we'll do it just by working these things out one by one. T of S of 1 is T of 2, which is 1. T of S of 2 is T of 3, which is 3. And the last one must be a 2. Let's just check it. T of S of 3 is T of 1, which is 2, as expected. Okay, so there are our two compositions, S composed with T and T composed with S. An important thing that you can notice there is that S composed with T is not the same function as T composed with S. For example, S composed with T sent 1 to 3, but T composed with S sent 1 to 1. They are different functions. So in general, permutations may not commute. That means that in general, S composed with T and T composed with S for two permutations, S and T, may be different to one another. Sometimes they'll be equal, but very often they'll be different. Okay, one final fact. So we've just seen a way in which permutations behave slightly differently to like multiplying real numbers, for example, multiplying non-zero real numbers, let's say. So non-zero real numbers, when you multiply them, they do commute. A times B is always the same as B times A. But for permutations, that's different. But there are a lot of similarities between permutation composition and multiplication of non-zero real numbers. For example, both of them are associative. For another example, they both have a special element, so the number 1 and the permutation, the identity permutation, which when you compose or multiply doesn't change the thing you composed or multiplied with. 1 times A is always equal to A, and the identity composed with S is always equal to S. Thirdly, they have the property that there are always multiplicative inverses. So you can multiply A and A to the minus 1 together to get 1, and you can compose a permutation with its inverse to get the identity. Because of these similarities, we will often talk about not just the composition of two permutations, but we'll also say the multiplication or the product. So we'll use the language of multiplying numbers to talk about composing permutations. And similarly, we'll often write ST instead of S composed with T, and TS instead of T with the composed symbol and then S, just like we write AB to mean A times B. So this multiplicative notation is very common when we're talking about permutations.